of stages is equal to number of unknown variables. Next, come to state. The difference between that we have to do substate. Number of is known as stage. Number of unknown variables equal to number of stages. And whereas state means whatever the calculation procedure we are going to do in that stages are called states. Means the calculation procedure. What type of calculation procedure we are going to do in the different stages is called states. Here, stage means is broken into number of problems, and each problem is known as stage. Stage is variable given problem. It also defines the portion of the problem that process is a mutually exclusive alternatives, each from which the alternative will be selected. It is known and coming to the state mode will state the bind of states there. And coming to the up the dynamic program, just I will the applications of the program is used to problems or of the situations is product enroll allocation of sources, equipment of of etc. Okay, next coming to characteristics. 1 minute. Let me discuss first characteristics of right. This is dynamic program. To the dynamic program. See, so the characteristics dynamic program may be outlined as follows. The problem can be divided into stages. A policy decision at each stage means how many unknown variables are there. Depends on that number of unknown variables, we have to divide the problem into that number of stages. And each stage, the decision required at each stage. And each stage has a number of states associated with it. So how many stages are there? That kind of number of states will be derived in that problem. So the theme of state is it will be connected with each and individual stages. Each stage has a number of states associated with it. And third one, the effective of the policy decision at each stage is to transform the current state into a state associated with the next stage. As this is most important, this third point, I will read once again. The meaning of the state is the effect of the policy decision at each stage is to transform the current state into a state associated with the next stage. Given the current stage, an optimal policy for remaining stages is independent of the policy adopted in the previous stages. Next one. The solution procedure begins by finding an optimal policy for each state of the last stage. And next, a functional equation is available which identifies the optimal policy for each state with n stages remaining. The given optimal policy for each state with n minus 1 stages left. And last point, using this functional equation, the solution procedure moves backward stage by stage, and each time finding the policy when starting at the initial stage. These are the characteristics of dynamic programming problem. Next. See here. Next, coming to the methods. In dynamic program problems, here we will discuss three types of problems. That is, what is objective function, the nature of objective function, and nature of functions. The problem can be divided into three types. So first one, single additive constant and multiple multiplicatively separable returns. It means the objective function will be multiplicatively returnable function, and constants will be additive manner. I given one example also. We discuss these three different problems in dynamic programming method. Single additive constraint, there will be only one that will additionally like that plus divided by n equal to center. So single additive constant and multiplicatively separate objective function should be either it may be minimum or it should be multiplicatively. Okay, like this here. I given one example also. So solve the following LPP by Bellman's, sorry, solve the DPP by Bellman's principle of optimality. The question will be like this: minimum z equal to up to yn. Objective function is multiplicatively separable return, and constant should be additively constants. That is STC. Subject to the constants are y1 plus y2 plus equal to b. And non-negative condition, each and every individual unknown variables must be greater than or equal to 0. That is yi greater than or equal to 0 for all a equal to 1 to n. So this is first one. Second method, single additive constraint, a single additive constraint and additively separable return. It means the in second method, objective function also additive function and constants also having additive function. For example, here mag equal to b1x1 plus b2x2. So plus divided up to bn xn means the objective function is in terms of additively separable return, and constants also in terms of additive, that is addition, that is x1 plus x2 plus divided up to xn equal to c. Okay, and a non-negative condition, of course this is common. Non-negative condition is how many unknown variables we are going to take, that all unknown variables must be greater than or equal to 0. And we have one more method, that is single multiplicatively constraint additively separable return. So here objective function is objective function is additive, that is minimum y1 square, for example here y1 square plus y2 square plus add up to yn, and constants are multiplicative constants, that is y1 into y2 into add up to yn equal to b, and all unknown variables must be greater than or equal to 0. So in our syllabus, three different types. So we'll do these three types of problems. One is, first method is additive constants. Subject to the constant should be additive in terms of addition, and multiplicatively separable returns. That is objective function should be in terms of multiplicative. Okay. For example, object minimum minimum constraints addition and objective function multiplicatively separable return function. That is objective function should be in terms of multiplication. This is method 1. Coming to the method 2. Yes, method 2. Constraints also in terms of addition and objective function also in terms of addition. That is additively constraints and additively separable return function. That is objective function also in terms of addition, constraints also in terms of addition. For example, minimum or maximum, what is it? Maximum is equal to y1 plus y2 plus right up to yn. So objective function I'm taking in terms of addition, and constraints are constraints also in terms of addition. y1 plus y2 plus y3 or y1 square plus y2 square right up to yn square equal to b. So and all variables are greater than or equal to y1 greater than or equal to yn is also greater to 0. This is and come to third type. We have third problem. Multiplicatively constraints. Constraint should be multiplication and object function should be that is multiplicatively and additively. Example, plus plus this third type. This optimal that kind of first constraint and probably the first method is additively constraint and multiplicatively separable return function. Second method, both are additives. That is constraints, additively constraints and additively separable return function. That is objective also addition in terms of. Next method, objective function, additively separable, additively multiplicatively separable. Objective function constraint should be multiplicatively separable, and additively separable returns. That is objective function addition, and constraint should be in terms of multiplication. So these kind of 3 model problems we will discuss. Let us discuss one problem with the completely with the help of this Bellman's principle of optimality. I'll show it. Here, the problem is solve the following dynamic programming problem by using Bellman's principle of optimality. So it is an example of case 3. Why? Because objective function case 2 is objective function in addition and constraints also in terms of addition. It is additively constraints and additively separable return. So in this, I'm taking only two unknown variables, x1 and x2. So within two steps, we can get variables each. We can obtain the solution for this problem within two stages only. See here. So what about coming to the solution? There are two variables in the given problem, hence it is solved in two-stage problem, or it is an example of two-stage problem. We know that the Bellman's solve this problem by using Bellman's principle of optimality. So we know that the Bellman's principle of optimality is, what is the formula? Just Fn of x equal to maximum of dn belongs to x is of r of dn plus fn minus 1 of t of x comma dn, where fn of x is nth optimality stage function value and dn is decision variables. X is the number of admissible variables and r of dn is immediate return function and fn of t, so t of x of dn is transferable function. So first come to the here n equal to here a capital, so just I am taking small n or capital what it may be. Let fn of them, what is our objective function? Maximum z is there. So I am assuming the question is giving maximum z. So fn of y equal to maximum of z. So we can solve this problem in exactly two stages. Why? Because here we have two unknown variables. So it can be solved, or the problem is in this, the problem is two-stage problem. So first, let us nth stage maximum z. One n equal to, we can get the solution. Here, next slide. If n equal to 1, come to the first stage. N equal to 1 means what is subject to the constraints? What about subject to the constraints? We have 2 40 and objective 5x2 and subject to constraints 2x1 plus x2 less than or equal to 430 and 2x2 less than or equal to 460 and the all x1 comma x2 are greater than or equal to 0. So by using this Bellman multi, I am substituting n equal to 1 first case. If you put n equal to 1 in subject to the constraints, we will get only first quantities, because n equal to 1 means we have to choose only x1 variable. So 2x1 equal to 430. In second equation, of course, there is no x1 value. So from the equation 1 only, we'll get the x1 quantity. 2x1 equal to 430. x1 equal to 215. Directly, I got first value x1. Here x2, 215. Therefore, what I assumed the general solution, let fn of y equal to maximum of z. So fn of y equal to maximum z. In first stage, fn of y will become maximum of among 2x1 plus 5x2, we'll get only 2x1 only. Why? Because n equal to 1. So fn of y will become maximum of 2x1. But I already got x1 value. What is x1 value? 215. So substitute that into in this equation. Fn of y will become 2 into 215 because x1 is 215. Therefore, in the first case or first stage, I got the solution is fn of y equal to 430. But I have two unknown variables. So I want to get f2y value also. For that, replace n equal to 2 in Bellman's principle of optimal. Equation 1. Therefore, if you put n equal to 2 in equation 1 and 2. So what is first equation? N equal to 2 means we have to consider two variables simultaneously. We have to take two variables simultaneously. So the first equation will become 2x1 plus x2 less than or equal to 430. That is 2x1 plus x2 equal to 430. And second equation 2x2 equal to 460. 2x2 equal to 460. Then x2 will become 230. So I got x1, x2 value. Substitute this x2 value into in this equation 1 so that we can get the x1 also. It is 200. So to this x1 is in our objective function. What is our maximum z equals 5? So I got x here. So f2 of 5 will become maximum of 2x1 plus 5x2. Therefore, maximum of 2 into x1. In this case, x1 is 100. Here I written the reason also see here. N equal to 2. The first two variables will get the first two variables only. Yes. That's why I have taken 2x1. So if we substitute x1 equal to 100, x2 equal to 230, finally we can get f2 of y equal to 1350. Therefore, the required solution is x1 equal to 100, x2 equal to 230, and the maximum z equal to 1350. This is about single additive constraint and additively multiplicative separable return function. Let us take one more example for another case. Here, this is what is our question? Bellman's principle of to solve the following dynamic programming problem. This is one of the most in your final exam. They will ask these kind of model questions. Please uh, Okay, okay. Ingara పెట్టు ఇక్కడ. Right. నేను అడుగుచుంటా. So here, let me discuss one problem based on additively separable function and constraint should be in multiplication type. Okay, I'll show it here. I'll share the screen. Yes. Solve this following dynamic programming problem by using Bellman's principle of optimality. So, what is the minimization function? As minimum z equal to y1 plus y2 plus yn, and subject to the constraints are y1 into y2 into y3 into divided up to yn equal to b. So totally I am going to take n unknown variables. Okay, y1, y2, yn, and objective function is in terms of addition. Constraint should be in terms of multiplications here. So it is an example of multiplicatively constrained and additively separable return function. This is method 3 examples here. So in the question they don't mention the method name, just they will give the objective and constraints. We have to, by saying, we have to decide it is so and so method. But whatever it may be method, each and every individual method, the procedure is common. Okay, so it is an example of case 3, that is multiplicatively constraints and additively separable return function. Means objective function is in terms of multiplication, that is minimum z equal to y1 plus y2 plus data up to yn, and constraints are in terms of multiplicative, that is y1 into y2 into y3 into up to data yn equal to b. And non-negative condition, all unknown variables y1, y2, y3 data up to yn are greater than or equal to 0. Okay, so now here the problem consists how many unknown variables? N unknown variables. Therefore, the problem, it can be solved within n number of stages. So first we have to divide this large problem with n unknown variables into some small sub problems like n1, n2, or y1, y2 up to yn. So here we have n unknown variables. So we can get the optimal solution within n stages. So this problem can be comprises factorizing a constant b into n factors such that the sum of the factors is minimum. It can be treated as n stage dynamic programming problem. Yes, I will repeat once again here. Here we have n unknown variables. Therefore, this problem can be treated as an n stage dynamic programming problem. So let the nth stage will be fn of b. So we need to calculate f1 of b, f2 of b, f3 of b up to dash fn of b by putting n equal to 1, 2, 3, 4 like that. Okay. So let fn of b the minimum attainable value of sigma I equal to 1 to n yi, means with all n unknown variables, sum of y1 plus y2 plus yn, where y1 comma y2 comma yn are factors of b. Next, that is fn of y equal to minimum z equal to summation of I equal to 1 to n, or y1 plus y2 plus that up to yn, or fn of y equal to minimum of y1 plus y2 plus that up to yn. Now we know that by Bellman's principle of optimality, for every problem we have to use this recursive equation only, or this Bellman's principle of optimality equation. For solving any kind of equations in dynamic programming problem, we have to assume the equation will be in this manner only. That is, by Bellman's principle of optimality, fn of x equal to minimum of dn belongs to x is such that minimum of dn belongs to x of r of dn plus fn minus 1 of T of x comma dn. I am assuming that is equation number 1. In this equation, we have to substitute n equal to 1, n equal to 2, that up to n equal to some loss n values. We can obtain the all individual stages value. We can get f1 value, f2 value, that up to fn. So stage 1. So first, this optimal solution can be done in n different stages. Yes. Therefore, fn of y equal to minimum z. If n equal to 1, we can get minimum z equal to y1. Minimum z equal to y1. So we need to find the y1 value in first stage only. In previously here, in previous problem, there we have two unknown variables. By putting n equal to 1 here, I will show once again this. By putting n equal to 1, we got x1 value. By putting n equal to 2, we got x1, x2 simultaneously. Like this, in this problem also, we have to find all n unknown variables y1, y2 up to yn by putting n equal to 1. First find the y1 value. By putting n equal to 2, we have to obtain simultaneously y1, y2 values. By putting n equal to 3, we can get the y1, y2, y3 values like that. Okay. Let me discuss first stage 1 procedure. So stage 1, if n equal to 1, the minimum of z equal to y1, because it is a combination of only single variable. First put n equal to 1. Of course, n unknown variables is there, but n equal to 1 means we have to consider only one unknown variable, that is y1. So n equal to 1, minimum z equal to y1, that is fn of y equal to minimum of y1. And coming to the subject to the constraints. So what is subject to the constraints? y1 into y2 into y3 into that up to yn equal to b. So put n equal to 1 means we will get only y1 equal to b. Okay. So directly I got y1 value. Each and every individual values will get in terms of b multiples because b is a constant here. So if n equal to 1, minimum z equal to y1 and fn of y equal to minimum of y1. And subject to the constraints, y1 equal to b. That is minimum of z. Minimum of z equal to y1, minimum of z equal to y1, and minimum of z equal to what is y1 value? I got that is b. So the first stage solution is f1 of y equal to minimum z, fn of y equal to minimum of yn, y1. So y1 I got that is b. So fn of y equal to b. This is first stage solution. Okay. Similarly, replace n equal to 2 or put n equal to 2 in equation 1 here. If n equal to 1, then objective function will become minimum of z equal to combination of two variables simultaneously, y1 plus y2. Minimum of z equal to y1 plus y2, or f2 of y equal to minimum of y1 plus y2. And come to the subject to the constraints. In previous stage, I have taken only n equal to 1. That's why I got y1 equal to b. But in this case, I am going to substitute, I am going to take n equal to 2 means simultaneously we will get the equation y1 into y2 equal to b. See here. I got the equation is y1 n equal to 2. Yes, n equal to, the constants will become y1 into y2 equal to b. And here we have two unknown variables, y1 and y2, but only one single equation. So we cannot solve this because the number of equations are less than 2 number of unknown variables. So it is highly impossible to solve. That's why I am assuming any one of the variable, either y1 or y2 equal to another variable in terms of x or z or k or whatever. So I am assuming y2 equal to x. If y2 equal to x, then the above equation y1 into y2 equal to b will become y1 into y2 equal to b. y1 into b, y2 means x. y1 into x equal to b, or y1 equal to b by x. So I got y1 value in terms of x multiples, y2 also in terms of x multiples. That is, if you put x equal y2 equal to x, I got y1 is b by x. Therefore, the solution will become f2 of y equal to minimum of y1 plus y2. So minimum of what is y1 y plus y2? I am writing this is y2 plus y1. Just I am assuming y2 equal to x. So minimum of y2 equal to x plus y1 and y2 plus y1. So what is y2 value? X, and y1 value b by x. So therefore f2 of y equal to minimum of s. Here I am taking the Bellman's principle of optimality formula. This is Bellman's principle of optimality. This is equation 1 formula here. Because if you want to know fn, if you want to calculate fn of x, we need to find out fn minus 1 values first. So fn minus 1 means in this case y1 is the fn minus 1 and fn of x means y2. So if you want to calculate f2 of x, we need to find out f1 of y. Already I got f1 of y equal to b. So I'm going to use this fn of y here. So f2 of y equal to minimum of x plus f1 of b by x, because the transferable function is in the statements here, Bellman's principle of optimality. T of x comma dn is transferable function. So the function is going to transform from where to where? Fn of y is, yes, Fn of y is b. Fn of y. It is going to transform from b to b by x, because I got y1 is b by x. Therefore, f2 of y equal to minimum of x plus fn of b by x. Since I written here from which condition I written like this? By Bellman's principle of optimality. Therefore, minimum of x plus f1 of b by x. That is f2 of y equal to minimum of x plus b by x. Now we have to find the minimum quantity for this single variable function. So we did these kind of model problems in 10th standard or intermediate standard. Whenever one single variable function is given, how we are going to obtain the minimum values for that one? That is, first to obtain the minimum value of above function. That is, what is above function? That is to obtain the minimum value of x plus b by x equal to 0. So how we can obtain the minimum value? In the school level or intermediate level, we did this kind of problems. In what way we are going to obtain the minimum quantity or maximum quantity for single variable constraint. That is, f of x equal to x square plus 2x plus 3 equal to 0. Let us suppose for that case, that equation, we are going to obtain the minimum quantity. Like, first take differentiation and find the roots by equating 0. Take the first differentiation with respect to the variable, whether it may be x or y or whatever it may be. So differentiate with respect to that variable and equating f dash of x equal to 0. And solve this equation, we will get the roots and substitute that roots into second derivative. Again, we have to go for the second derivative, f double dash. In this f double dash of x, we have to substitute the roots, whatever the roots we got, and substitute that roots into f double dash x. If f double dash x value must be less than 0. Yes, listen carefully. F double dash x is less than 0 at so and so point, then it indicates that at that point, the given object to the given function has maximum quantity. Why? Because f double dash x is less than 0 at x equal to so and so. Means at x equal to so and so value, the given function has maximum, because it is f double dash must be less than 0. Suppose f double dash x is greater than 0 at x equal to so and so quantity. It indicates that the given function has minimum value. Why? Because it got greater than f double dash x is greater than 0 at x equal to so and so quantity. It indicates the given objective function has minimum value at x equal to so and so. So by using this rule, this principle, I will going to obtain the minimum quantity. In the question itself, is giving minimum of x plus b by x. See here, take differentiation, equating them into 0, find the roots and substitute the roots into in the given function that indicates greater than 0, then obviously it will goes to minimum quantity. Yes, I will explain that calculation procedure by sharing the slide here. Here. So first we obtain the minimum value of above function. That is, to obtain the minimum value of what is our function? X plus b by x equal to 0. Assume this is fx. Let us take differentiation. So x plus b by x equal to 0, differentiate with respect to x, because here x is the independent variable. Differentiate with respect to x. so that it will become x differentiation 1, b is a constant, 1 by x differentiation is minus 1 by x square, which is equal to 0. So 1 minus b by x square equal to 0. If you solve this equation, b by x square equal to 1, or x square equal to b, or x equal to plus or minus root b, or x equal to plus or minus b by 2. But here in the question itself, he is saying it should be minimum. Just I am taking the x equal to, actually we have two roots. Let us take positive root, x equal to plus b by plus root b. So y2 I already assumed y2 equal to, what is y2 value? Y2 equal to x, then I got y1 is b by x. But already I got x value. What is x value? Root b. So substitute these x values into y2 and y1, so that we will get the both unknown variable values simultaneously, y1 and y2. So if you put x1 equal to, sorry, x equal to root b, x equal to root b, we'll get y2 equal to root b, and y1 is b by x. B by x means b by root b. B by root b means if you bring this root b into numerator, it will become y1 equal to b into b to the power of minus 1 by 2. So bases are same, powers can be added, means b to the power of 1 minus half. So it is y1 equal to b to the power of 1 by 2, that is root b. So with the help of this x equal to root b, I got x1, y2 equal to b to the power of 1 by 2, and y1 also b to the power of 1 by 2. Now substitute these y1, y2 values in our objective function. What is our objective function at the stage 2? At the beginning, I assumed what is the objective function? Yes, f2 of y equals here. The solution, f2 of y equal to minimum of y1 plus y2. So substitute these two values in this equation, so that we'll get a substitute y1 and y2 values in the objective function. f2 of y will become f2 of y equal to minimum of y2 plus y1. Minimum of y2 is root b, y1 also root b. So it is b to the power of 1 by 2 plus b to the power of 1 by 2. So it is 2 times of b to the power of 1 by 2. So I got y2 of y equal to 2b to the power of 1 by 2. So in stage 2, the solution is f2 of y. Like that, we have to find n stages solution. So here n unknown variables are there. Then how many times we need to take? N times. So it is very lengthy process. So I just up to 2 stages I got y f1y, f2y, and similarly you can do, we'll get the f3y, and we will get the f4y, like that. But instead of doing all n stages, just find out, is there any relation is going to exist in stage 1, stage 2 solution, or stage 2, stage 3 solution. See here, instead of taking, yes, listen carefully, instead of taking n times, just I did up to 2 stages, f1 and f2y. So I got f1y equals so and so answer, f2y also I got so and so answer. Then we need to take one more stage, f3 of y, one next stage, f4 of y. Like that, we have to take up to fn of 5 stages. So instead of doing n stages simultaneously, before going to take the next, at least do 2 or 3 stages. Instead of going fourth, fifth stage, just check the is there any relation is going to exist stage 1 and stage 2, in between stage 1 and stage 2, or in between stage 2 and stage 3. With the help of that, we can estimate. Similarly, we can get fourth stage value is so and so value, fifth stage is so and so value. Like that, we can estimate. Okay. So here I got first stage value is b to the power of 1 by 2. Second stage is 2 into b to the power of 1 by 2. And let me, is there any relation exist? If it is not, then go for the one more stage value, that is f3 of y. And with the help of these 1 or 2 or 3 stages, definitely we can get the one recurrence relation. We'll get the one relation among the stage 1, stage 2, how it will be going to develop the function. Like that, we can estimate the nth stage value also so and so. So for getting that relationship, I will do one more stage here, F3 stage. I'll share it. Here. So up to stage 1, I got answer is f1 of y equal to b. and f2 of y equal to f1 of y equal to b, and f2 of y, I got the solution is second stage f2 of b equal to 2b to the power 1 by 2 here. This is f2 of y. So similarly, let me do one more stage, n equal to 3. If you put n equal to 3, the objective function will become, what is our objective function? Sum of attributes, that is sum of variables, that is up to n unknown variables. Therefore, f3 of y will become combination of y1 plus y2 plus y3. See here. So f3 of y equal to, see the solution, if n equal to 3, yes, f3 of y equal to minimum of y1 plus y2 plus y3. And what about subject to the constraint? The constraints are in terms of multiplicative. That is y1 into y3 into that up to yn equal to b. So if n equal to 3 means simultaneously we have to take 3 multiplications. y1 into y2 into y3 equal to b. With the help of that, we can obtain the third solution stage 1. See here. Therefore, n equal to 3, I got subject to the constraint is y1 into y2 into y3 equal to b. Again, in this also see here, we have only one single equation, that is y1 into y2 into y3 equal to b. But we have totally 3 unknown variables. So we cannot solve these equation. Why? Because the number of unknown variables are more than 2 number of equations. We cannot solve. For solving this, let us assume any one of the variable equal to some x. That is, I am assuming y3 equal to x. If you put y3 equal to x, then we can get the remaining 2 variables in terms of b by x. That is y1 into y2 into y3 equal to b. Therefore, y3 equal to x means y1 into y2 into x equal to b. Therefore, y1 into y2 equal to b by x. So I got y1 into y2 is in terms of b multiples. Now substitute y3 value and the product of y1 y2 values in equation, that is f3 of y solution. So f3 of y equal to minimum of y1 plus y2 plus y3. Therefore, again I'm writing this is f3 of y equal to, first write down y3 first, next write down the remaining 2 combinations. Minimum of y3 plus y2 plus y1, and which is equal to f3 of y equal to minimum of, I got already y3 value. What is y3 value? X. If you put a y3 equal to x, then I got y2 is combination of y1 y2 is b by x. So minimum of x plus, that is y3 plus x plus y2 plus y1, and I'm going to write these two y2 plus y1 as a combination of b by x. That is with the help of which formula? Bellman's principle of optimality. f3 of y equal to minimum of x plus f2 into b by x. f2 of b by x. Yes, is it clear? f3 of y equal to minimum of x plus, that is y3 plus y2 plus y1 means x plus y2 plus y1 is, it is a second solution. Already I got y2 plus y1 value. That is f2 of b by x. Since by Bellman's principle of optimality. So what is f2 of y solution? Already I got f2 of y solution is, see here, in previous n equal to 2 stage. f2 of y equal to 2 times into b to the power of 1 by 2. Now I am going to use this value here. So f2 of y equal to 2 into b to the power of 1 by 2. But what I want to find, I don't want to find f2 of y. I want to find f2 of b by x value. So f2 of y equal to 2 into b to the power of 1 by 2. With the help of this, f2 of b by x will become 2 into, wherever b is there, just replace. The function is going to transform b by x to 2 into b by x. Okay. So the transferable t of x common tn function in this case is b to b by x. Okay. So f2 of b by x equal to 2 into b by x whole to the power of 1 by 2. So here the transferable function, here I written here. Here the transferable function is from where to where? B by x to 2 into b by x whole to the power of 1 by 2. Okay. Then the f2, f3 of y will become, substitute this value into in this f3 of y. Therefore, f3 of y equal to minimum of x plus f2 of b by x. Minimum of x plus f2 of b by x value is, what is f2 of b by x value? Yes, it is 2 into b by x whole to the power of 1 by 2. So minimum of x plus 2 into b by x whole to the power of 1 by 2. Again, we have to find the minimum quantity for this single variable function. Just now we did whatever the procedure we did here for obtaining the minimum quantity. Take substitute differentiation and equating 0, find the roots and put the roots into solution like that. Similar procedure I will going to obtain here also. So obtain the minimum value of the above function. What is our function? X plus 2 into b by x whole to the power of 1 by 2. So for that function, I am going to find minimum quantity. So apply the school level or intermediate level procedure, whatever procedure we studied in earlier. That is, differentiate with respect to x first. Therefore, x differentiation, it is 1 and 2b whole to the power of 1 by 2 is constant. So 1 by x to the power of 1 by 2. So 1 by x whole to the power of 1 by 2, if you bring x into numerator, x to the power of minus 1 by 2. So for this equation, we have to take the differentiation. So differentiate with respect to x means for 1 it is, for x it is 1 and plus 2b to the power of 1 by 2, x to the power of minus 1 by 2 differentiation, n into x to the power of n minus 1. That is minus 1 by 2 into x to the power of minus 1 by 2 minus 1, which is equal to 0. So 1 minus, it is plus into minus minus, 2 to cancel, b to the power of 1 by 2 into x to the power of minus 1 by 2 minus 1 means minus 3 by 2, which is equal to 0. Bring this and solve it and find the roots. So x minus b to the power of 1 by 2 divided by x to the power of 3 by 2 equal to 0. So from this, b to the power of 1 by 2 x to the power of 3 by 2 equal to 1. And finally, x to the power of 3 by 2 will get b to the power of 1 by 2 and x equal to b to the power of 1 by 2 and bring this x to the power of 3 by 2. 3 by 2 power into right side, it will become 2 by 3. So 2 get cancelled, we'll get x equal to b to the power of 1 by 2. So in this case, by applying the minimum function of obtaining the minimum quantity, with the help of this formula, I got x equal to b to the power of 1 by 2. So substitute this x value into y3 and y1 y2. Obtain that values. So I got this entire procedure by assuming y3 equal to x. If you put y3 equal to x, we got y1 y2 equal to b by x. So substitute x value in this case, we'll get the y3 value as well as y1 y2 values simultaneously. See here. Substitute x equal to b to the power of 1 by 3 because I got x value. What is x value? B to the power of 1 by 3. Substitute x equal to b to the power of 1 by 3 in the objective function. Then we can get f3 of y equal to minimum of x plus b by x whole to the power of 1 by 2. So minimum of x, x means b to the power of 1 by 3 plus 2 into b by b to the power of 1 by 3 whole to the power of 1 by 2. Okay. Therefore, minimum of, if you take complete simplification, it will become b to the power of 1 by 2 plus 2 into b to the power of 1 by 2, 1 minus 1 by 3 to the power of 1 by 2. So total we will get b to the power of 1 by 3 plus 2 into b to the power of 2 to get cancel. Again, it is 1 by 3. So b to the power of 1 by 3 plus 2 into b to the power of 1 by 3. So total we will get 3 times of b to the power of 1 by 3. So finally I got f3 of y equal to 3 b to the power of 1 by 3. Okay. This is third stage solution. Like that, we have to take fourth stage, fifth stage, and up to nth stage. But instead of doing all and each and every individual stages, just check out is there any relation is going to exist in among first and second, or second and third, or third and fourth solution. See here. What about first solution? I got first solution is, yes, what is first solution? Here. First solution f1 of y. I got f1 of y equal to, what is that value? f1 of y is, see here, f1 of y equal to b. And what is second solution? f2 of y is 2 into b to the power of 1 by 2. And I got f3 of y. f3 of y is, what is f3 of y? Third solution. f3 of y is 3b to the power of 1 by 3. With the help of this, we can obtain the one relation here. First solution, f1 of y equal to b. So, let b is a 1 into b to the power of 1 by 1. Yes. Next, f2 of y. f2 of y is 2 into b to the power of 1 by 2. And f3 of y. f3 of y solution is 3 b to the power of 1 by 3. So that is, I'm going to write f3 of b is 3 into b to the power of 1 by 3. Means, what is the variation here? First solution, b coefficient is 1 and b to the power of 1 by 1. Denominator is also 1. And second solution, 2. That's why I'm taking 2 into b to the power of 1 by 2. Denominator is 2. Similarly, third solution f3 of I is 3 into b to the power of 1 by 3. So we got one relations here. Similarly, if we extend this solution up to fourth stage or fifth stage, definitely we'll get f4 of y equal to 4 into b to the power of 1 by 4. Fi of y equal to fifth solution, 5 into b to the power of 1 by 5, and so on. Similarly, the nth stage solution can be obtained definitely Fn of y equal to n into b to the power of 1 by n. Okay, this is the recurrence relation formula of solution. With the help of this given dynamic program problem, finally we got the optimal solution is Fn of y equal to n into b to the power of 1 by n. Okay, this is nth stage problem. So in this question we have n unknown variables, and each and every individual variable values, with the help of that each and every individual variable values, I got f1 solution, f2 solution, f3 solution. With the help of this, I prepared one recurrence relation or one relation among these solutions. Finally, I got f4 value, f5 value, and fn value is n into b to the power of 1 by n. Okay, this is about Bellman's. So with the help of this Bellman's principle of optimality, we can find the solution for each and every individual value. Okay, okay, sir, I'm going to stop. So like that, we have to find the solutions, whether it may be 2 unknown variables or 3 unknown variables or n unknown variables. With the help of these Bellman's principle of optimality, we can obtain the solution. Okay. Remaining one method we have, we will discuss that method in next class. Okay. Tomorrow also we have one class. In the next tomorrow next class, I will going to explain that multiplicative objective function additive constant problem. Okay. Let me do that kind of problems next class. Okay. Let us stop. Let us continue next class. Okay, thank you. Let us continue next class.